In this video, we are going to explore the algae blooms dataset using Ggplot2. I'm going to be following a pipeline, a flow established by Torgo in his data mining with R book. I do change a few things here and there, but it's a good way to show you how to use Ggplot2, but also how you can use data visualization to help you gain a sense for the data set that you are studying. We're trying to predict the presence or absence of various algae in water and rivers based on a number of properties. The reason why we want to do this is because being able to monitor and perform early forecast for these algae blooms is crucial, right? It helps you control the ecological harm that they can cause. The observations in our data sets are a bunch of samples that have been selected at various rivers, various locations around Europe. We have chemical properties for these samples. We have characteristics of the rivers themselves, or at least the sampling sites within the rivers. And we have the actual quantity of, 7 algae, as the case may be here, for each of the samples. So why would we even want to build a prediction model to try to predict the presence or absence of algae blooms? Couldn't we just analyze the samples, or analyze any water sample we take and determine if there's algae blooms or not? Well, the answer is actually quite simple, and in fact it's a very pragmatic answer. Chemical monitoring is cheap. It is easy to automate. But biological analysis, determining if you have living algae in the samples, is actually fairly expensive and slow. So if we could, with the help of a few chemical tests, computing the pH, for instance, seeing how much phosphate is in the water, if we could predict the presence or absence of the algae before we take the sample to the lab to be tested, this could be quite advantageous. There's another answer as well. If you just analyze the samples for harmful content, it doesn't give you an understanding of what we call the algae drivers, what causes algae to be found in water. All it does is it tells you which samples contain algae. So if you're able to build a predictive model, not only would you be able to make predictions about the presence or absence of algae without having to take samples back to the lab, although you can also do that, but you'd be able to try to understand what factors lead to there being. So I have saved a data into a data set called the algae blooms data set. And I'm going to start right off the bat by actually calling the read.csv function to load the data. And we see here that the data has been loaded. Well, what kind of a data set do we have? It's never a bad idea, no matter what you're doing, to take a look at the structure of the data set. And we're seeing here, let me scroll up a little bit, that our data set is a data frame, that it contains 340 observations. We already knew that from this here. 18 variables, ditto, we also knew that. And there's a number of variables, 3 of which are categorical: the season, the size, the speed. These are the river characteristics of location when you took the sample. You have 1, 2, 3, 4, 5, 6, 7, 8 chemical properties. There are chemists among you. You might recognize that these are chemical properties, if you want, of samples. The presence or the concentration of various compounds. And then there are your 7 biological components, the presence or absence of various algae. You get perhaps a better sense, even a better feel for the data frame if you call its head. Let's see what the first few observations look like. Alright, so I have my signature here and the corresponding presence or absence of algae. One of the things is we do not have a lot of information about the domain. I barely recall having taken a chemistry course years and years ago. It was an introductory survey course. I gotta say, like, without domain knowledge of this, I mean, I worked as a lifeguard when I was a teenager, and I had to sort of test the water. I recognize pH in there. I don't recognize any of these other things other than by, knowing that Cl is probably chlorine, and NO3NH4, there's some sort of ammonium in there, some phosphate for the PO4, but I don't really know what any of these things mean. So given that I do not have domain expertise, either on the chemical side or on the biological side, I'm going to use some data exploration to try to get a sense of the problem at hand. It can't replace domain expertise, and if I was serious about trying to make this predictive model, I'd have to get the help or enlist chemists and biologists and river specialists at some point. But in the absence of that, data exploration can help me build a superficial understanding of the data and of the problem. So one of the ways in which you can do that is by calling the summary function. Like, the head function gives us the first few lines, but it doesn't really help us find any potential issues. Let me scroll back up here to see what the summary function gives me. It looks as though amongst the measurements, they're roughly spread out equally amongst the seasons. That makes sense. For the size of the river, the speed of the river, they are not spread out equally, but perhaps this is representative of the actual landscape of the rivers in Europe. There's a few other things you might notice just by looking at this summary. All of the numerical values, so if I look away from the three factors here, all of the numerical values are positive. It's sort of nice. But I'm getting some weird ranges. I'm finding the fact that there's a river with a pH of 5.6 to be problematic, and a pH of 9.7 also problematic. So these ones look problematic, but since I don't know what these other values should be, I can't say that they're problematic enough. Although, to be fair, if I look at this maximum here for NH4, it is a good 2 orders of magnitude greater than the mean. Base R comes in with a bunch of pre-built visualization functions. What do you think this function will be? Well, I'm just going to try to build a histogram of the MnO2 variable in the algae blooms data frame. Let's run it to see what we get. And you get the histogram right here. Frequency count, the various levels that you may have. It looks like it's going from 0 to about 14. Does that match with what we had for MnO2? Let's scroll back up a little bit. There's your MnO2. Actually, yes, it goes from 1.5 to about 13.4. This is what I'm seeing here. You look at this histogram and you would conclude that whatever the underlying distribution was for the variable MnO2 could not be a normal distribution, right? This distribution is skewed. It couldn't be normal, period, because all of the values are positive. In fact, they have to be positive because you're measuring the presence of something. So that cannot be a normal distribution, but it could have been approximated by a normal. The fact that we see a fat tail here says, no, this is probably not a normal distribution. There's a negative skew. Well, you can spruce up this, this histogram a little bit. I'm going to do so by calling the Ggplot2 library. That's important if you want to use the ggplot functionality. You need to have loaded the Ggplot2 library. So I'm going to build a plot here. So from the slides, you've seen that you first need to call the ggplot function on the data set of interest. and you need to set or fix an aesthetic mapping. So here, the X variable will be the actual value that we're trying to plot. The geometry that we're going to be plotting is a histogram. And it's going to be a histogram where we have a density instead of a frequency count. We're going to add a new geometry, which is going to give us the density curve, or the approximate PDF, probability density function. Let's color it blue. I'm going to add to that a rug. A rug is going to show me exactly where the observations fall, even though I'm going to be producing a histogram, and the rest of it, well, is the title of the histogram together with no labels for the x-axis and no label for the y-axis. Let's run this and see what we get. Well, there's an error message, or at least a warning message. It is telling us how many bins it's using, bins 30. It's reminding us that we could specify the number of bins that we want within the histogram call here. And it turns out that we had 2 rows that have missing values. These have been removed. This is what the histogram looks like, but because I called the density option, I'm seeing this here as a probability value, not an actual frequency count. Right, so we're seeing here, this is the rug showing us where the observation, the measurements are, and we're seeing, it seems to be concentrated here. It makes sense. Where there's more of a distribution, you would expect to see more of the observations. And the tail, well, even though like the histogram gives us the impression that there's a lot of observations, we're seeing exactly, no, it is a bit of a tail here. Compare that to the original histogram, we get the same shape, but we don't have the same number of bins, mind you. Same shape. And it's pretty clear here that this cannot be a normal distribution. But it wouldn't be that bad of an estimate to assume that the distribution is normal if we compare it, say, with the histogram of one of the algae. We'll look at algae A1. So what do we have? We're going to be plotting a grammar of graphics plot on the algae blooms data frame, and the horizontal value, the X value, will be mapped to the level A1. Okay. We're plotting a histogram. Again, we want it to be a density plot, not a frequency count plot. We're going to have a curve of density. We'll color it red. We'll still put the rug. And here, well, I have a different title because I have a different variable. Let's see what we get. This is obviously not a normal distribution. In the previous case, you could, if you squinted and took a few steps back, you could sort of treat this as a somewhat almost symmetrical distribution. Why not model it with the normal distribution? But you could not do this with the distribution of the A1 values. And what you're seeing is that there's a fair number of the samples in which there's barely any A1 algae. And, a sizable tail of measurements where we do have. If you recall, when we looked at the summary, I spent a bit of time highlighting the fact that at least one of the ammonium values, the NH4 values, seemed like way off base. Let's take a bit of time here to see if we can explore that a little bit more. We're going to build a box plot. We're going to build a box plot out of the algae blooms dataset. The variable of interest on the vertical axis, the y-axis, will be the NH4 measurements. Here I set up a very specific X measurement because I want my box plot to show up in one column, but you don't necessarily need this in general. I'm going to want to add to that a horizontal line, this guy here. And we'll do so we'll set it up. Let me show you the rest of the code here. The horizontal line will be found at the value of the mean for all the NH4s. Because we have some missing values in the NH4 variable, we need to compute the mean by removing the values that are missing. And the rest of it, the line type equals 2 and the color is pink, just, aesthetics related to the actual. Alright, well, that doesn't look like much of a box plot. Right, I do see my horizontal mean here, and I'm just seeing some suspected outliers and this sort of weird thing. So let's see what the box plot looks like with this new smaller data set. Well, we purposely removed the very large observations for this level, for this variable. Okay, now we're seeing the box part of the box plot. The line, the horizontal line, which was meant to be at the mean value, it has shifted because we have removed some of the big values, right? Before we had here somehow, but if you look at it here, all the value is at a different location. It's shifted down. And the range, so it only goes to 3,000. That's not surprising because we've removed everything which is greater than 3,000. Now what you're seeing here is that there are still a fair number of large NH4 values. Is that normal? I have no idea. I don't know anything about what to expect on that front. How would you find out if this is normal or not? Presumably this isn't something you can find out from data analysis alone. But it has allowed me to ask a question, which is, roughly speaking, what are the reasonable values of NH4 to have in water samples? I wouldn't have known to ask this question before. I mean, you should be asking these questions all the time about all the variables. What are the reasonable values to have? But now I have a very specific question to ask. You can do other things. You can take a look at the algae levels, but let's do it on a seasonal basis. Is it the case, for instance, that algae are in bloom in specific seasons and that their levels are lower in other seasons? Look, algae are plants. Plants typically have some sort of reaction to the seasons. Is that going to be the case for the algae? What I'm building here is a box plot. Notice the aesthetic. I have two aesthetics. I have the A3 variable, so that's going to be my vertical variable, the algae level A3, so not A1, A3. My X value is season, and now what the output is I'm going to have a box plot for each season. Whereas in the previous case of box plots, my X value was factor 0. This was telling it I just want one box plot. So what does it look like to you? Is there going to be a relationship between the season and the algae levels for A3? It certainly seems as though, visually, there is some link. But it's actually hard to get a good handle on the situation because the seasons are out of order, right? How are the seasons ordered here? They're ordered alphabetically. That isn't really what you would expect from your data set. I mean, you'd like potentially spring to be the first factor and then move on to summer, autumn, fall, or winter to get a better sense for it. So you can do something like that. You can reorder the levels by loading the forecast package and by loading the dplyr package. Let's do that. What we're saying here is we want, well, we'll do it for size, for speed, and for season, because now we've realized that it seems to be alphabetical order which carries the day. We'll want the river sizes to be small, medium, large in that order. The levels to be low, medium, high for the speeds in that order, and spring, summer, autumn, winter for the seasons. And now if I plot the same box plot as before, so now the order sort of makes sense. And I am seeing, perhaps as I would expect, that there is a dip in the presence of algae in the autumn. So spring seems to be where the algae bloom the most. Starting dipping in the summer, full dip in the autumn, and gearing back up for the spring and winter. We only have 1 year's worth of data here, so perhaps it's too early to tell what's really happening, but it does seem as though there's a bit of a reasonable pattern. Alright, so there seems to be a link between the presence of one of the algae, and you're welcome to try the other algae, and the season. Is that also going to be the case for NH4? So let's go back to the original data set. We're going to keep only those observations for which the level is above 3,000. So eventually, I'll uncomment this thing. So what's happening here is we're filtering the algae blooms data set by keeping only those observations for which it is not the case that NH4 is an Na, so we're getting rid of all of the missing values. Then we further filter by passing it through the pipeline the result of that original filter by removing all of the observations which are above 3,000. So we only keep those that are below 3,000. And then we will mutate this, which is to say we're going to create a new variable which tells us in which of the quartiles the measurement really is. Is it in the first quartile, so the smallest 25% of the observations, and then in the second quartile between 25 and 50% in terms of size, third quartile, and the 50th and 75th percentile, and finally in the fourth quartile, meaning that it's in the top 25% of values. Right, so let's take a look. We'll just filter this data. That's done. If you wanted to see how many observations we had, you might compute the number of rows. We have 327. Now, it's not obvious from looking at this call here, but if you just call it that way, you are not going to be including the lower bounds of the actual quartiles. And so there's two measurements of NH4 that have value 0. They're not going to be included here. So in fact, what you want is to have a slightly different call. Just type it in for you here. In essence, you want to tell R that they should include the lower bound. Just rerun this. Fair enough. Now let's do a nice plot. Alright, so this is a data set that we filtered. We're going to want to have on the horizontal axis the algae 1 level. On the y-axis, we're going to have the season, which we will double as an element by also using the color. We're going to create a scatter plot, basically. We're going to have facets, which means that we are going to produce a different plot for each of the quartiles in our data, right? So we're going to use the variable q.nh4, which basically told us in which quartile we were found for the NH4 measurements. And there's going to be one different plot for each of those, and we'll just give it a title. So that's going to be trying to see if there is a link between the NH4 quantity, the season, and the A1 level. You get the following chart. What are you seeing here? It seems as though the A1 levels, which are the horizontal quantities, are inversely correlated with the NH4 levels. But the season doesn't seem to have that much of an effect. Like basically, the values you get on each row here is roughly speaking, the same sort of distribution. But the lower the level of NH4 given by this quartile, the higher the corresponding A1 values seem to be. This doesn't do much in the way of providing evidence here. But again, this is allowing us to ask the question, is it likely to be the case that the NH4 level is an inhibitor for the algae A1? This is not a question I could have asked with any degree of seriousness before doing the data exploration. You can also ask the same thing about the algae A3. What would you conclude from such a graph? I wasn't trying here to provide you with all the answers to all the questions. All I wanted to do was to show you that it's possible to explore a data set and to get to the point where you can start asking smart questions of the experts, even if you have no domain expertise to start with. Take the time to look at the variety of examples I provide in the notebooks. The more practice you get, the better you will be at creating your Ggplot charts, and the better sense you will get for the dataset.